So Newton's method can be very effective at finding zeros of a function. It can also have a couple little pitfalls. If you look at the formula here, if the derivative ever happens to be equal to 0 at your guess, then this will be undefined. You won't be able to get a next guess, so the method will stop. So in this case, you think that's possible. If we had a function like this and we're trying to find this this intersection here, the 0 right here, if we happen to guess this value right here, at this point the derivative is 0. Remember, the idea of Newton's method is to follow the tangent line back, but if the tangent line has 0 slope, then you're not going to be able to proceed to the next step. Also, Newton's method may not converge, and this particular example has been cooked up to show a situation where Newton's doesn't converge. Let's we have this piecewise function. Let's calculate the derivative. If x is less than 2, then we take the derivative, the 1/2 comes down, we get 2 minus x to the negative 1/2, and then the derivative of the inside will be negative 1, which will cancel that negative. So we'll have 1 over 2 times the square root of 2 minus x. If x is greater than 2, we could use this formula, and that will give us 1 over 2 times the square root of x minus 2. So if x is equal to 2, then the derivative is going to be undefined. But if x is equal to 2, that's actually the fixed point of this function, or the 0 of this function, because if you plug in 2, 2 minus 2 is 0, and the square root of 0 is 0. So 2 is actually the 0 of this function. Okay, so we've got the derivative. Now the next thing that we need to calculate would be f of x over f prime of x, which again, that will be undefined if x equals 2. But if x is less than 2, we'll have this function dividing by this fraction is the same as multiplying by its reciprocal. So we're going to get negative 2 times, if you take the square root of 2 minus x times the square root of 2 minus x, you'll just get 2 minus x if x is less than 2. And if you have f divided by f prime when x is greater than 2, you really have the square root of x minus 2 times the reciprocal of this, so you get 2 times x minus 2. If we, when x is greater than 2, or I could simplify one more step. We have negative 4, and then minus 2 times minus x would be 2x minus 4, and here we have also 2x minus 4. So we're getting the same thing either way, whether x is less than 2 or x is greater than 2. So that means that our next guess, x sub I plus 1, is going to be our current guess minus this. That's going to be minus 2xi minus 4, as long as we don't guess 2, which simplifies to xi minus 2xi plus 4, which would be 4 minus xi. So our next guess is always 4 minus the current guess. So if we were to guess, say, 3, then our next guess would be 4 minus 3, and then we'd have 4 minus 1 would get us back to 3, and then 4 minus 3 would get back to 1. It just keeps oscillating back and forth. We never get a solution. So you can see what's happening in this case. It's, we've pieced together these two functions. So if we started, say, at 3, follow the tangent line back, we get 1, and then we find the tangent line there, and follow it back, we're back to 3. So we just keep cycling between 1 and 3. We get a 2 cycles. So it's possible that Newton's method may not converge to a particular value. Another thing that happened is that Newton's method might converge very, very slowly. So here's an example. Let's figure out what Newton's method says. We need to calculate the derivative, which would be 40 times x minus 1 to the 39. So f of x divided by f prime of x is going to be x minus 1 to the 40th over 40 times x minus 1 to the 39th. That's going to be 1/40th of x minus 1. So if we look at what Newton's method says, it says our next guess, x sub I plus 1, is going to be our current guess, x sub I, minus 1/40 of x sub I minus 1. So our next guess is going to be, let's see, we have x sub I minus 1/40 is going to be 39/40 of x sub I plus 1/40. So we can see that the solution here is 1, right? So the only way to get 0 out of this function is 1. And but we look at this, we're going to take our time getting to 1. If we start with 2, then our next guess is just going to be, let's see, if you take this times 2, you have 78/40 plus another 40, is 79/40. So basically we started with 2, that's 80/40, so we got to 79/40. This is getting to 1, but it's going to get there very, very slowly. Let me actually show you in Excel here. We can program this. We had a guess starting at 2. Let me wipe out what we had before. Now the formula is to take 39/40 and multiply that by the current guess, and then add 1/40. And the solution is 1, but see how slow we're going? Okay, it's taking many, many steps. We're still not there. Keep pasting the formula down, getting more and more guesses. We've taken 61 steps, and we're not even very close to the answer, which we can tell is 1. So what's happening in this case is we have a very flat function. The function's very flat as you approach 1. So you calculate a tangent line and follow it back. And since the function's flattening out, you don't make it very far before you have to do the next tangent line, and so on. So because you have a very flat function near the actual solution, the 0 is right here at 1, it can be very, very slow to converge. Another problem that can happen is that Newton might converge to a number, but it might not be the one that you were looking for. Here's an example. We have this function, and there are actually 3 solutions, one here at -2, one at 0, and one at 2. So you'd think that if you started at a value, say, that was more than 1, that should eventually converge here. But what will actually happen in this case, what can happen is, if you start here, you could have this tangent line carry you all the way over onto this other side, and then from there you're going to converge to this -2. So you get tangent lines that bring you back here, and then another tangent line, and so on, get to -2. So even though you thought you were starting pretty close to this value, it should have converged to that one. It actually jumped over and converged to this other one. So just because it converges doesn't mean that it's the only solution, and it may not even be the solution that's closest to where you started. So just a couple things to keep in mind about Newton's method if you're using it.